Yeah, hello everyone. Thank you for joining. It is my pleasure to introduce Dr. Muhammad Izhar, who is an assistant professor of mathematics at Government Postgraduate College, Mardan. Dr. Izhar earned his PhD in mathematics from Abdul Wali Khan University, Mardan in 2019, with the research focused on the application of set theory in decision making. His academic interests on decision making in commutative algebra, and he brings with him more than a decade of undergraduate teaching experience across colleges in Khyber Pakhtunkhwa. So today, Dr. Izhar will guide us through cryptography, the big picture. Um, yeah, so please join me welcoming Dr. Muhammad Izhar. Over to you, Dr. Singh.
Thank you, Wajid, for so kind introduction. Uh, my talk is on cryptography. So let me let me share what we will cover in this talk. We will learn what is cryptography. I will share a historical cryptographic scheme and which is now a basis for the modern cryptography. Then I will discuss about the discrete logarithmic problem and which is the basis for the Diffie-Hellman key exchange. The Diffie-Hellman key exchange is basically based on the discrete logarithmic problem. And then I will discuss the elliptic curve cryptography, and that is also based on the discrete logarithmic problem. So actually, the two schemes both are based on the discrete logarithmic problem. So let us start our discussion. Whenever we open WhatsApp, so we see this end-to-end encryption, and by this WhatsApp means that it wants to keep our messages secret, so that the third party cannot read our messages. Our data should be safe from third parties. Likewise, the security agencies want to share their most sensitive plans without being exposed. So how do they do it? How they pass their secret messages from one quarter to another quarter without being exposed to third parties, to the enemies. So the main concern is how can we share information securely without the fear of leakage or interception. This is the main problem, that how information should be can be transferred from one quarter to another quarter without being exposed to the third parties. So the solution for this problem is encryption. And in encryption, even if the data is intercepted by the third party, they cannot read it because it has been coded in a manner that the third parties cannot read it. By encryption, we mean that a process which converts readable information, which we usually call plain text, into unreadable information, which is known as ciphertext. And how do we do it? It is used by using a secret method or key, so that unauthorized people cannot read our messages, or that only authorized people can read the messages. And cryptography is the science of designing such methods to secure our information and to transform the information from one place to another place, and to transform it into unintelligible form to unauthorized parties, while still allowing the intended recipients to recover and use the original data. So encryption means how to transfer a readable information to cipher information to an unreadable form. And the science that does this all for us. That is known as cryptography. Let me share about the very historical encryption scheme that was used in ancient times. The diagram that we are seeing is known as Caesar Cipher. So in this, the we shift each letter by some fixed number. For example, in this case, the outer circle shows the plain text and the inner circle shows the cipher text. So if we move the key by 19, so A is shifted to T. So if our message contains a letter A, it will be encrypted to T, B will be coded to U, C will be coded to V, and etc. The shift can be anything. So in this example, I have taken the key as 19. Let us see a small example that suppose an army commander wants to convey this message attack to a battlefield. So this is our plain text attack. Now looking at this Caesar cipher, the A is shifted to the word T. So A will be replaced by T. Likewise, T is coded to M. So the both T's are now read as M. A is again replaced by T. We can see here C is coded as V. So C is replaced by V and K is replaced by, we have shifted all the letters by a specific number, 19. So K is shifted to 19. So if the commander wants to convey this message attack, he will convey TMMTVT to the battlefield. So if anyone reading this text will not be able to understand, even if they intercept the message, so they cannot decrypt this, they cannot understand what does it mean. Now, when this message reaches to the battlefield, they will again use the key 19 and they will shift back every letter T. So small t will be decrypted to A, M will be decrypted to, here you can see the small m, that will be decrypted to T and so on. So TMMTVD will be recovered as attack. So this was the plain text, this is the cipher text. By the rule, by shifting by letter 9, by shifting all the letters by 19, this was the key encryption rule, and so the other party will shift backwards by 19, and that is the decryption rule. So this is how in ancient times they encoded their messages. But here is a very basic flaw. For example, if we can see that there are only 26 choices. So like if the enemy starts to try with the key 1 and then 2 and then 3, for example, if they want to decrypt this message, so when they reach 19, so they will get a meaningful letter which is attack, and the message will be the secret will be exposed to the third party. So this method, although it is a very important method, because the modern cryptography is totally based on this concept that there is a key, there is encryption. So this is the basis for the modern cryptography, but this was not very, although it is used, but to decode a message by brute force, somebody, anyone can decode the message. So like you see that both the parties must know by what number to shift. For example, in this case, it is 19, and this key should be kept secret. This is the main objective of my talk, that I will talk on that how can we secure this key, how can we share this key securely, that no third party can know about this. Like I should reiterate my point that, for example, decryption and encryption is an easy task, and sending this message from one place to another place is easier. But the main thing is to keep this key secure. If this key is shared with anyone, So all the messages will be read by any other, if anybody intercepts it. So and if they know this key, so they can decrypt the messages easily. So the point is that encryption is not an issue. The main issue is this key, that this key should be shared securely. For example, the person who is uh, taking the message from here, from one place to another place, and he somehow discloses this key to the enemy. So the encryption process and all that, the army or anyone who wants to keep the messages secret will have no value. So my talk is about the exchange of this key, that how can we exchange this key securely. So like I said, that the problem is that the sender and receiver must agree on a key in advance. And if the enemy somehow knows the key, so they can read the secret messages. So the main issue is that the key should be securely exchanged between the two parties. This is the central problem in cryptography, that how do two parties share a key securely. So there are two techniques. The two techniques are, the first one is known as symmetric key exchange scheme, and the other is known as asymmetric key, or also known as the public key. So in the symmetric key exchange, I will briefly say like that both the parties in advance have exchanged a key, and now they are using the same key. And the asymmetric key is that every time they can exchange a new key, both the parties have different keys. In asymmetric keys, both the parties can choose their different keys, and they can both the parties have a different secret, and they can share then the key securely. So both the parties do not agree on one code. So how will we do this? So my talk is about that in asymmetric key exchange, there are three schemes: the RSA, the Diffie-Hellman, and the elliptic curves cryptography. So I will talk about the discrete logarithmic problem, the Diffie-Hellman scheme, and the elliptic key cryptography. That how we can exchange the keys by using these techniques. Now, the first thing is that we should know about the discrete logarithm. What do we mean by a discrete logarithm? Let us go back to this group, that we know that the group of residue classes under addition modulo n is given by Zn, which contains these elements from 0 up to n minus 1. Now, if we form another set from this Zn, which we denote by Zn star, and we choose all the elements from this set that have the GCD 1 with n, we choose all the elements from this Zn that has the GCD 1 with n, like I have written it here. We collect all those x in Zn star, and it is well known to the undergraduate students that this forms an abelian group under multiplication modulo n. Like in Z9, if we see 1 has GCD with 9, 1, 2 is relatively prime with 9, 4 is relatively prime with 9, 5, 7, and 9. So this is a group under multiplication modulo 9. Now, if we choose P a prime, then for every prime P, this ZP star, the units in ZP, forms an abelian but a cyclic group. And we know that a cyclic group, what is a cyclic group? A cyclic group is a group in which there exists an element G such that every element in that group can be obtained as a power of G. Like every element X can be expressed in this power, G power I, for some integer I. And this G is known as the generator of the group. Like for Z23 star, the generator is 5. Now, this is the main thing to understand, that what is a discrete logarithm. So if we are given a finite group ZP star, and of course it has order P minus 1, because 0 is excluded from this set. and we are given a generator of this ZP star. So if we are given any other element and we are asked to which power G is raised so that we can obtain X, which power of G would give us X? So if we transform this problem to the logarithmic notation, so this is the same as the I is said to be the logarithm to the base G of X. So the integer I is called the discrete logarithm of X to the base G, and we formally write it as I is equal to log to the base G of X mod P. So this is actually what discrete logarithm is. This is different from the ordinary logarithm. This is the discrete logarithm. I hope so. The things are clear. Now I have taken the group Z47 star, and I have chosen the generator G is equal to 5. And suppose we want to compute the log of 41 to the base 5. Since it is the generator, so some power of G must give us 41. So we start taking the powers of 5. 5 power 1 is 5, 5 power 2 is 25, and when we reach 5 power 15, sorry, I forgot to write 41 here. It should be 41. It is 41. So 5 power 15 gives us 41. There is a typos. So please forgive me for this. This is 5 power 15 becomes 41. So we can write that the log of 41 to the base 5 is 15. This is what the discrete logarithm is. Now, the point to ponder about is that the discrete logarithm is very hard to find. And how can I support this statement that the discrete logarithm is hard to find? In small primes, we can use the brute force and try all the powers. Like in Z47, there we can take the powers up to 47 and eventually we will get 41 somewhere. But if the prime becomes large, then the brute force attack is impossible. So when I say that the DLP is a discrete logarithm, why do I say that the discrete logarithm problem is very hard? So the main reason for it is that no efficient algorithm is known so far. This is the one problem. This is the one point which should be understood, that no efficient algorithm is known. And if we choose a prime like this, 2 power 2 power 2048 bit prime, so the group size would become 2 power 2048. And if we now try to compute all the exponents, so we would have 2 power 2048 exponents. And if a computer could do a trillion exponents per second, it would take longer than the age of the universe. So if we choose a 2048 bit prime, the modern day computers cannot break this problem. They cannot the, find the discrete logarithm. Although there are some known algorithms, but their order of complexity is only square root p. So there are 3 known algorithms which are used to find the discrete log: the baby step, giant step, the Pollard's rho for DLP, and the index calculus. And this is only applicable to certain groups. So the discrete logarithmic problem is a very hard problem to solve. Now, Diffie-Hellman utilized the discrete log concept, and they developed a scheme through which they can exchange a key securely. So how do they do it? I will explain in the next slide. Here's a brief introduction of the Diffie-Hellman key exchange, that it is proposed by Diffie and Hellman in 1976. The two inventors were influenced by the work of Ralph Merkle. It is a public key exchange algorithm. Like I said, that it is asymmetric. Both the parties have their own secrets, and they will exchange a key with that. Both the parties have their own secret key. And the basis for the Diffie-Hellman key exchange is the discrete logarithmic problem. The one problem with this is the man in the middle attacks. What does it mean? So it is a technical term. The man in the middle means that if anyone can come in the middle, and he can send the messages to both the parties, and he can intervene in to obtain the key. So this is a technical term. The person who is in the middle, and he can send messages to both the parties, and he can know about the key. So this is vulnerable to the man in the middle attacks. Now let us try to understand what the Diffie-Hellman key exchange problem is. So we choose the ZP star group, which is from 1 to p minus 1. So P is known and the generator G is known. So these are the public parameters. Uh, the P and G are the public parameters. Now two parties, one is Alice and other is Bob. He chooses his secret number A and Bob chooses his secret number B. With the help of A and B, they will now exchange a key securely. How do they do it? Uh, Alice have chosen his secret A, so he sends this message G power A mod P to Bob, and Bob sends him G power B. Now Elias obtains G power B, so he takes his secret key G power A to G power B, and he obtains G power AB. And like Bob has received G power A from Elias, now he raises it to his own secret key, which is B, and he gets the same number G power AB. This is that key. Now the problem is the third person who is Eve, who is the observing the whole process. He only sees these three numbers: G power A, G power B, and G. But it is super hard for him to calculate G power AB, and this is basically the discrete logarithmic problem. So the Diffie and Hellman have used the discrete logarithmic problem. A common key is exchanged to both. He chooses his secret A. He has his own secret B. He sends him G power A. He sends him G power B, and he calculates G power B power A. So this is the whole scheme. If you can read it again and again, so anyone can understand it. But the point is that the man in the middle knows about G power A, G power B, but it is super hard for him to calculate G power AB from these three information. And this is actually the discrete logarithmic problem. This is a concrete example, so I want to skip this. Let's study it. Z23 star is a group which contains 1 to 22 elements and which has generator 5. Now the prime P is 23 and the generator is 5. The LS has chosen his secret key A, and Bob has chosen his secret P. So Elias raises G to the power A, which is 5 to the power 4, and which becomes 4 because the multiplication is mod 23. So we get 4. He sends 4 to Bob. Like you can see here that Elias has sent 4 to Bob. Likewise, the generator has been raised to the secret chosen by Bob. It is G power B. So he raises 5 to the power 3, and we obtain 10. And Bob sends 10 to Elias. Now Elias raises 10 to power 4, and Bob raises 4 to the power 3, and they both have the common key. What Eve has observed is that he observes A, B, and G, but now it is very hard for him to obtain these A and B from only this information, G, A, and B. So this is the main this is the Diffie-Hellman scheme for exchanging the key exchange, and the man in the middle cannot find what key they have shared. Although he's seeing this information, the whole information is going through a public channel, but Eve cannot find what key has been exchanged between the two persons, are the two parties. So this was the Diffie-Hellman key exchange problem. How the Diffie-Hellman ensures the exchange of a secure key between the two parties. This is only a pictorial diagram. Anyone can see this after the talk and try to understand it by himself. The advantages of the Diffie-Hellman is, again, as I said, its security is based on the hardness of the discrete logarithmic problem. And if we choose primes greater than 2048 bits, it is computationally infeasible to break this. And the strength is that it provides a key exchange between the two parties. These are the advantages, and some limitations that the man in the middle who can send unauthenticated messages to both the parties, and he can know about the key. So this is vulnerable to, and this can be overcome if authentication is added. So then the man in the middle cannot know about the key. The other limitation is that it requires expensive modular exponentiation. So it is slower than the symmetric key encryption, and the key sizes must be very large for security. So sometimes constrained devices may not be able to deploy the Diffie-Hellman key exchange. And the quantum algorithms, quantum computers are a threat for the Diffie-Hellman key exchange in future. So these were some limitations and some strengths of the Diffie-Hellman scheme. Now, the modern technique for the key exchange is the elliptic curve cryptography. So let us first know what is cryptography. Let me just go back to the slides that the Diffie-Hellman scheme is actually based on choosing a cyclic group with a generator. So in the elliptic curve cryptography, we will replace this group ZP by any arbitrary group. What will be that group? So we will see now. So first, let us learn what an elliptic curve is. So an equation of this form, y square is equal to x cubed plus ax plus b, with a, b are rational numbers. This equation is known as elliptic curve. The graph of this function is like this. This is an example of an elliptic curve. You can choose a and b from any rational numbers, and we get an elliptic curve. So elliptic curves, where does this name come from? So when we compute the arc length of an arc on an ellipse, that leads to integrals that cannot be evaluated in terms of elementary functions. And these integrals were called elliptics. So the name was then carried over to the curves on which they naturally lie. And anyone who wants to study about the elliptic integrals that lead to elliptic curves, they can read this book, Why Ellipses Are Not Elliptic Curves, published in, they can read this book. So let us now introduce an addition operation, and under this addition operation, the points on the elliptic curve form a group. So how do we define the addition of 2 points on an elliptic curve? So suppose if we choose 2 points on an elliptic curve and we join them, so it will cut it in the third point. We take the reflection of this point in the y-axis, and this point is known as a plus b. You may be wondering why such a weird addition has been deployed here to form it a group. So this dates back to Defontis, and he was looking for the rational points. So whenever he chose 2 rational points on the curve, and he joined that by a line, and it cut it in another point that was also a rational point. So and the reflection of that point was also a rational point. So this is the idea behind that. They define the definition of the addition operation is like that. If we choose 2 points a b, we join them by a line and take the reflection of this point, and this becomes the point c, which is equal to a plus b. Now, a natural question arises that if both the points are same, So how can we add them? So if 2 points are, if 2 points coincide, what if B is equal to A? So if both the points coincide, so when we approach B to A, we will get a tangent. Now it cuts it in another point and we take the reflection of this point, and this operation is a closed binary operation. Whenever we choose two rational points on the curve, we get another rational point, and this is due to De Fontes work. Now this is addition. For a group, we need to have an identity element. So how do we add an identity element in this group? So let's, for example, here I choose a point A and I want to look for a point which when added to A, and we are here back on A. So we introduce a point at infinity. So like if you, the point at infinity is usually denoted by O. So like you join A with O, it cuts the point, the curve in this point, and when we reflect this, we get back to A. So if we add A with O, we get back to A. So this is an artificial point which is not on the curve, but this serves as an identity element for the curve. Let us see it again. Like this is A point. If we add it with a point at infinity, it will cut the curve in this point, and when we reflect it, we get back to A. So the point at infinity work as an identity element. Now the next point is that how do the inverses look like? So now again, look at this. There is the point A, and we want to see that what should be added to A so that we get O. So if you now, for example, if you add A with minus A, so if we extend it, so this is the point A. So when we add A to the minus A, we will get this point at infinity, and now A and minus the point right above the curve, the point right above the point A is minus. We call it minus A, and it is the additive inverse of the point A. So this is the how the addition and is defined, the identity element and the inverses look like. So this is now the elliptic curve, and we don't prove it like, but the set of all points with together with the special point at infinity with this addition rule forms an abelian group.
How do you define the multiplication with the point at infinity? The addition with the point at infinity. Can you repeat that, please?
Yeah, I am a bit confused in this. Like, let's discuss it. For example, this is the point A. Now we look for a point which gives us what should be added with A so that we can obtain the point O. Like, uh, let's see what A and minus A gives us. So if we add A with minus A, sorry, Shah, I have lost a bit. This point, I've just lost a bit here. Let me think, and maybe at the end we can discuss it again. That how
So,
this minus A serves as the additive inverse of how minus A serves as the additive inverse of A. Very apologies.
I think you want to say the following. So you take a line through A, and then the line, of course, goes to infinity, but it intersects the curve somewhere. And that point, when you reflect back, might not end on A, but there is at least one line where it intersects the curve at a point such that if you reflect that point, it would come back to A. That's where you can call minus A. So I think there's a unique such line. And that's, I guess, how you
If you, this is very clear. For example, this is the point O. And when we add, sorry, when we
No,
add,
the point O is at infinity, so you can take any line from A and that line would go to O because
yeah,
yeah.
yeah.
But now
So
you want to find one line that goes from A to infinity, but when you intersect it with the curve, it should be reflected back to A,
yeah, 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 yeah.
right?
Yes,
And there
yes,
is, I think,
yes.
a unique such line.
Yeah, yeah. But yes,
So
you are
I
right.
mean, I'm not sure, but I think that probably is
This
the
is
way.
this is how, for example, the definition is that what should be added with A, so that we end up in O. This is the definition of the additive inverses. So the addition we define is that we choose 2 points. Like if we choose these, let me think. If we choose these 2 points, it goes to infinity and it cuts. It meets here and we reflect it, so we get back to minus A. So when we add these two, we get zero. But we may discuss it after the talk. I don't know why the things have skipped from my mind, but I'm so
But I
sorry.
think the easy way is to take any point and then just reflect it. So that gives you another point, which you call minus A. And the line passing through the two would go and intersect the curve at infinity.
Yeah,
Yeah, that's how
yeah,
it should work.
yeah. A plus minus A is O. So the additive inverses are very easy, and the points right above the point A serves as the
So,
additive inverse of.
and since this line is vertical, it would never intersect the curve somewhere else, right?
Yes, yes. Since the line is vertical, so it will never meet the curve.
No.
So this is how the addition, the identity, and the inverse have been shown, and this forms a group. Now, for our cryptography purposes, we choose the elliptic curve over a finite field, like the elliptic curve over a finite field like ZP, and the prime is any number greater than 3. So the set of all pairs xy from ZP cross ZP which fulfill this equation together with the point at infinity forms a group, and we will play with these points. The set of all the points on the elliptic curve with this addition, but uh, the coefficients are also coming from ZP, and the solutions are also sought in ZP cross ZP. So this forms a group, and we will deal with this group. So the explicit formulas by which we can add 2 points is, this is the mathematical formula by which we can add P and Q. So if there are 2 points P and Q on an elliptic curve, and the elliptic curve is taken over any field FP, so this is the formula by which we obtain X3 and Y3. So if the points are distinct, we calculate S by this formula, and if the points are the same, so S is calculated by like this. And the division should be understood that x2 minus x1, like this is division, but we will compute y2 into y1 into x2 minus x1 inverse, and the inverses exist in ZP. So this is how the computation will be done. This is 3x1 square plus a divided by 2y1 will be computed as 2y inverse in FP. So let us see an example that how can we um, double a point. This is a very small illustration. So if we choose this curve y square congruent to x cube plus 2x plus 2 mod 17, the field is Z17. And suppose we choose this point 5, 1, and we want to double it. So we want to find P plus P. And now the formula, the S will be calculated by 3x1 square plus A like this. So we have calculated S by, and as you can see, 2y1, so the inverse in ZP is calculated, and this goes on to 13. This is S, the X coordinate is now 6, and the Y coordinate is now 3, and so The point is 2p. Why I'm not seeing it here? The point p is, can you see the point here in the end of the slides? The point is calculated in
Yes,
the end of,
I see it.
okay. So this is 2p. So this is how we do computation on an elliptic curve. So this is a brief introduction that who introduced this. We can skip this. This is a small example again, that if we choose this curve, y square is equal to x cube plus x plus 1 and mod 5. These are the solutions, and these points form a group, of course, a cyclic group with the generator p 0 1. So if we do p plus p, we will get this point, p plus p plus p this, and the whole group is generated. This group has 9 elements. This is the last part of the talk, and now we have replaced the group by the group of points on the elliptic curve. This is the same as the Diffie-Hellman problem, but now this is called the elliptic curve Diffie-Hellman problem. Just the group has been generalized to elliptic curve. There the group is a fixed group ZP star, and here the group is now the elliptic curve group. So we choose an elliptic curve E. The set of points on the elliptic curve, we form a group, and we choose a base point, which is usually a generator of a cyclic subgroup of that group.
You mean the set of rational points, right?
Yes. In essence, these are the rational points, but now these are the solutions, like Shavi said, like this. The elliptic curve group is the set of all points that satisfy this equation. So we cannot say now rational points, but the idea is the idea of the defaultness. So now we are dealing with the solutions from ZP cross ZP.
Okay.
So these are like here you can see the points are not rational, but from F5 across F5. So again, Elias has his own secret A, and he computes the base point may be public, E may be public. Elias has chosen his secret A, and he computes A times P. We have defined how can we compute A times P by adding P A times. And he sends it to Bob. So Bob will multiply B with this, and he will obtain ABP. Now Bob has chosen his secret B. He computes BP, and when he sends it to Elias, he will multiply it with A. So both have shared their common key, which is ABP. So any person who is seeing this information, A, B, and P, if he knows about the base point as well, so he cannot compute K, and this is again due to the discrete log problem. And elliptic curve cryptography has many advantages over the like the Diffie-Hellman, classical Diffie-Hellman scheme. There we have chosen 2048-bit prime, but now in elliptic curve cryptography, we can choose only 256-bit prime. And for students who have not studied, who cannot understand what do I mean by 256-bit. So this only means that a prime with 93 digits, and by 2048 we mean that a prime with 927 digits. So that is a very big prime, and now the digits have been reduced to 93. So any 93 digit prime can be chosen. Like in RSA we have to choose the 3072-bit prime. So the Diffie-Hellman, so the elliptic curve cryptography, the Diffie-Hellman analog of when we choose the elliptic curve group, so we can choose a prime very small, up to 93 digit long, and the same security will be ensured. So smaller keys, if we choose smaller keys, so computations can be faster. It can reduce the storage, and It is for constrained devices. This is very useful. This is the modern technique which is nowadays used, and this provides a strong security today and is more efficient for integration with post quantum approaches. In post quantum approaches, there is another technique, there is another scheme that is going on, that is the lattice based cryptography. So I was studying about the lattice based cryptography, and that is actually trying that if a quantum computer is built, how can we then securely exchange the keys over an insecure channel. So this is another topic of interest, lattice based cryptography. Anybody who is interested, he can study about it. And this was this is the end of the talk. I hope so. This was good.
Yeah, it was excellent. Thank you very much for that insightful talk. Yeah, I really enjoyed it.
Thank
A
you.
lot of
Thank you.
a lot of new things. Yeah, so we now have some time for questions and
Yes,
maybe
please. We will try to
some
answer.
discussion. If you would like to ask a question, just please raise your hand or type it in the chat, and we will unmute you. So, and maybe I will just hit stop recording.